Welcome to this engaging introduction to graph theory, which stands as one of the most fundamental concepts in computer science and mathematics, providing essential tools to understand and model all kinds of connections between different entities in our world. As we dive in, you'll see how graphs help us represent relationships in everyday scenarios, making complex ideas accessible even for beginners new to these topics. Picture a bustling social network where individuals are linked through friendships, or envision a detailed city map that illustrates the network of roads connecting various locations, allowing us to navigate from one place to another efficiently. These intuitive examples showcase how graphs capture pairwise relationships in real-world situations that we encounter daily. Indeed, these are practical, real-world manifestations of graphs, which are precise mathematical structures specifically designed to model and analyze pairwise relations between distinct objects, whether they are people, places, or any other entities. Graphs enable us to study connectivity patterns systematically, forming the backbone for numerous applications in computer science. At its core, a graph is composed of nodes, also known as vertices, which represent the individual entities or points in the system, and edges, which symbolize the direct connections or relationships linking these nodes together. This simple yet powerful structure allows us to visualize and manipulate complex networks with clarity and precision. Importantly, these edges or connections can be either directed, much like a one-way street that permits travel in only one direction, or undirected, similar to a two-way road where movement is possible in both directions between the connected nodes. Understanding this distinction is key to accurately modeling different types of relationships in graphs. Gaining proficiency in navigating and traversing these graph structures is absolutely crucial for a wide array of computer science applications, from network analysis to artificial intelligence, as it allows us to efficiently explore and extract meaningful information from interconnected data. Whether optimizing routes or analyzing web links, traversal skills are indispensable. In today's video, we will thoroughly explore two of the primary and most widely used methods for traversing graphs: breadth-first search, commonly abbreviated as BFS, and depth-first search, or DFS, breaking them down step by step for beginners. By the end, you'll have a solid grasp of how these algorithms work and when to use them. To begin our deep dive, let's focus on breadth-first search, or BFS, which is a versatile algorithm that methodically explores a graph by progressing level by level, starting from a chosen source node outward in expanding waves. This approach ensures a systematic visit to all nodes based on their distance from the start. Breadth-first search initiates its exploration right at a specified starting node, and then promptly visits every one of its immediate neighboring nodes, marking them as explored before moving further. This first layer of neighbors represents all nodes directly connected to the start, forming the initial frontier of the search. Once the first level of neighbors has been fully visited, BFS then systematically advances to explore all the neighbors of those newly visited nodes, expanding to the second level, and continues this outward progression layer by layer in a highly organized manner. This level-by-level expansion guarantees that closer nodes are always processed before farther ones. This iterative process of level expansion persists relentlessly until every reachable node within the graph has been visited, or alternatively, until the specific target node that we are searching for is successfully located and identified. At that point, the algorithm can conclude with optimal results for certain problems. To manage this orderly exploration, BFS relies on a queue data structure, which operates on a first-in, first-out, or FIFO principle, keeping track of the nodes queued up for visitation next and ensuring the breadth-wise progression remains intact. This queue acts as the algorithm's memory, preventing revisits and guiding the search efficiently. You can think of BFS as akin to exploring an intricate maze by meticulously checking every possible path that is exactly one step away from your current position, then all paths precisely 2 steps away, progressively increasing the distance in a methodical fashion. This analogy highlights the algorithm's commitment to proximity-based discovery. One of the hallmark applications of BFS is its ability to determine the shortest path between any two nodes in an unweighted graph, where all edges are considered equal in length, making it the go-to choice for distance minimizing problems. This property stems directly from its level-by-level exploration strategy. Having covered the essentials of BFS, now let's transition our attention to depth-first search, or DFS, an equally important algorithm that employs a contrasting strategy for graph traversal, diving deep before branching out. We'll examine its mechanics in detail next. Like BFS, DFS commences at a designated starting node, but rather than spreading out level by level, it plunges as deeply as possible along each available path or branch before considering alternatives, prioritizing depth over breadth. This creates a more adventurous, exploratory path through the graph. DFS commits to fully exploring one particular path from the starting node all the way to its conclusion, whether that means reaching a dead end with no further unvisited neighbors or encountering a node that has already been visited previously. Only then does it consider redirecting its efforts. Upon reaching such an impasse where no additional progress is possible down the current path, DFS performs backtracking, retreating step by step to the most recently visited node that still possesses unexplored branches or connections. This backtracking mechanism allows it to systematically cover the entire graph. This cycle of deep dives followed by strategic backtracking repeats iteratively across all branches until every single reachable node in the graph has been thoroughly visited and accounted for. The result is a complete traversal, albeit along potentially longer individual paths. In practice, DFS is typically implemented using a stacked data structure, which follows a last-in, first-out, or LIFO principle to manage the sequence of nodes awaiting visitation, or equivalently through recursive function calls that mimic the stack behavior naturally. Both methods effectively handle the depth prioritization. A fitting mental model for DFS is navigating a maze by selecting one promising path and pursuing it relentlessly to its farthest extent, only retracing your steps upon hitting a dead end, and then trying a different route from the nearest junction point. This mirrors the algorithm's deep-thin backtrack rhythm perfectly. DFS shines in scenarios such as detecting cycles within a graph by identifying back edges to visited nodes, identifying separate connected components that form isolated subgraphs, and tackling puzzles or problems that typically admit just a single unique solution path. Its depth focus makes it ideal for these tasks. To wrap up our comparison, both BFS and DFS serve as powerful foundational tools in graph traversal, yet their ideal applications diverge based on the precise nature of the problem at hand and the desired outcomes. Specifically, BFS proves ideal for scenarios demanding the shortest path discovery or when the priority is to explore and process nodes in order of increasing distance from the starting point, leveraging its breadth-wise guarantee of minimal steps. It's unbeatable for unweighted shortest paths. Conversely, DFS is frequently the preferred choice for challenges necessitating exhaustive, deep exploration, such as performing topological sorting on directed acyclic graphs or enumerating every possible path between a pair of nodes comprehensively. Its recursive nature suits memory-efficient deep dives. In summary, graph theory offers a remarkably versatile and robust framework for modeling, analyzing, and understanding a vast array of relational structures prevalent in computer science and beyond, from social networks to biological systems. To contrast them visually, BFS methodically explores the graph broadly in expanding layers from the source, while DFS delves profoundly into individual branches before backtracking to explore alternatives, each excelling in their respective domains. Mastering these fundamental algorithms, BFS for breadth and proximity, DFS for depth and recursion, represents a critical milestone in comprehending and tackling the diverse, complex computational problems encountered in computer science education and practice. Thank you sincerely for joining us on this enlightening journey into the captivating and foundational world of graph theory, where we've demystified graphs, BFS, and DFS for beginners. Feel free to revisit and practice these concepts to solidify your understanding.